Hey everyone. How's it going? All right. So this will be the last lecture that I give because I'm going to make an announcement about this later today so that everyone's aware officially. And I hinted to it on Monday's lecture, maybe it was Friday's. But for this coming Friday, the way the lecture is going to look is I'm very excited. I have confirmed there will be four guest speakers, uh, various researchers, graduate student researchers in the Department of Computer Science, who are going to be coming to give talks, these like little 15-minute presentations about what it is that they actually do, so that you can see that there's more to programming than just solving problems that I give you. There's a lot of cool stuff happening out there, and I think that these talks are going to be some great windows into many of the very exciting and cutting edge domains that people are using programming to push the boundaries of. So yeah, that'll be and then so after those mini lectures, there'll be a quiz as usual. That'll be the last quiz. And that quiz is going to be pretty simple compared to the other quizzes that we've had so far in the course. It'll be like I think right now the way it's going to look is going to be one programming question about recursion stuff. And then there will be four questions, one like sort of like free response questions, one for each mini talk that will be given on Friday. And these will just be like super easy questions about, what it is that they kind of do. Uh, and that'll be the whole quiz. Yeah, it should be really, really easy. Any questions about that or the program for the rest of the week? Okay, cool. All right, nice. Okay, then, in that case, let's get to what's probably on everyone's minds, this recent assignment. Okay, so before any of like the class officially started, there was already a request to see problem five. Do we want to, are there any other problems that we would like to prioritize? I don't know if we have the time to go over all of them today. We're going to try our best. But are there any other problems in particular that we want to prioritize going? Yeah. Okay, three and four. So three and four, five. Um, were the first two? Oh yeah, Kevin. Okay, two. Okay, so two, three, four, and five. Any? Somebody's going to be like one, and then another person's going to be like six. And we just go through the whole thing. Okay, but yeah, sure. We can focus two, three, four, five. Let's go over those. And I guess just in the interest of going in order of kind of maybe the way that they're stated here, we can just sort of start with problem two. Okay, yeah. So we kind of saw the palindrome checking problem back in the assignment on loops. Right? I don't know if any of you guys remember this. And it's a cool illustration of the fact that for any problem where a recursive solution is possible, you can also do an iterative solution. And we had the iterative loop-based solution a couple assignments ago. But this time around, it's saying, no, you're not allowed to use for loops or while loops or anything. You have to solve it recursively. So, okay, let's see how to do that now. We're going to make a new Python file that I will call problem underscore two. And we're going to make some function called isPalindrome. And it accepts a string called s. Okay, so how what is kind of the recursive structure of the palindrome problem? Right? Like how, because I mean, in general, when we think of solving problems recursively, there's usually like one big problem that contains, in some sense, some nested structure of subproblems, right, on smaller instances. And what does that look like for palindrome? Maybe like what is the base case and how do the inductive steps build upon each other? Yeah. Yeah, okay, it's exactly right. So there's going to be two base cases. It's going to be the base cases are when the length of the input string is one or zero. And in both of those cases, what should we do? What should we return? Because this is, but the function is going to return either true or false, right? So yeah, exactly. It'll return true. So we're going to have, okay, if s is equal to the empty string, or actually, let's do it this way. If the length of s is equal to 0, or the length of s is equal to 1, then we just return true, right? This is going to be our base case. Whoa. Base case right there. And now the question is, okay, what does the inductive case kind of look like for this recursive problem? So, okay, we've established that n, the variable of interest that is going to vary across our levels of recursion, is the length of the string, right? So, okay, suppose you're given an is palindrome function that works, and let's let n be equal to the length of our string. So let's say that you're given an is palindrome function that works on any string s of length at most n minus 1. How do I solve is palindrome on a string of length n in that case? Any suggestions on how we could go about this? Yeah. You did what, sorry?
You check the remaining.
And what's the remaining? Okay, so yeah, you're saying that we check if there are one or two.
It's one of the base cases. Check it.
Oh yeah, the base cases were good, right? Where we handle the base cases. Now we're looking at the cases other than the base case, right? Okay, well, maybe to kind of see this, it helps to it's like recursive problems are like Matryoshka dolls, right? There's like tinier versions of the problem contained in the big problem, and they look very, very similar. And it's turtles all the way down until you get to the base case where you know how to solve it trivially, right? So let's actually look at an example of a palindrome instance and see if we can identify some nested subcase that resembles the structure of the original problem. Where's my chalk? There it is. All right, so we're going to start with everybody's favorite palindrome, race car. Unless there's another suggestion for a palindrome that you're particularly passionate about. Any other? No, okay, then we'll do race car. Okay, so this is a palindrome, right? And we can check like, oh yeah, R, A, C, and E. Symmetric, right? But in order for race car to be a palindrome, is there some smaller substring contained in race car that, yeah.
Well, I mean, the R's so
Exactly. If I remove this, see, race car being a palindrome is the same as saying ASCA is a palindrome, and the first and last letter are the same, right? So there we have our inductive step. We're just going to check, we're going to call our is palindrome method or function on this substring, and then just check if the first and last letters match. Yeah? Okay, so let's see how to do that. So we're going to have, I guess one way we could go about this is we could say, first we're going to check, here's what we could do. We could say return S sub 0 equals S minus 1. So this right here, this checks if the first letter is the same as the last letter, right? And what else has to be true? We're checking if the first and the last letter are the same, right? We've done that, but another thing has to be true for it to be a palindrome. ASCA has to be palindrome, right? So the question then becomes, well, how do I access that specific substring? We could use a slice, right? The slice notation. So we'll just say and is palindrome S from 1 to -1. So this substring chops off the first guy. It just skips the first character and it excludes the last character, right? Because the up to index in slicing is exclusive. Yeah. And that's all there is to it, right? We check that the first and the last thing match and that the thing in the stuff in the middle is a palindrome, right? Yeah, question.
Yeah, isn't three back to its palindrome, and that can make an issue if like it'll return true if it's 0 or 1. So true basically.
Oh, you're saying like, will this always return true?
Well,
Because this always returns true.
well, like if it just so happens that the values happen to or like if it's 0 or 1. Right.
It's a 0 or 1.
Like for the case of like we're here, I don't know, maybe I'm misinterpreting it here, but it's like removing the the first mass value, hitting our value, then it's checking again, it's basically sort of fixing. But for the inner values, and if there's a 0 or 1 there, then in this function.
Wait, what do you mean if there's a 0 or a 1 there?
Oh, I'm sorry. Wait, I misread that. You're right. It just says the length of that.
Okay, cool.
Is it?
Cool.
Yeah.
Yeah, nice. Yeah, question.
Are we in this program, are we obliged to do everything in the return, or can we like kind of do the things?
Oh, no, no. So I did it like this because it was a bit of a shorthand, but maybe a more explicit way of writing this out, if you want, is we could say, okay, first, and I think this is actually the way I typed it up in the solutions. We can say first, last match. This is a Boolean variable that checks that my first and my last characters match. And then we can have another Boolean variable that says, well, the substring is a palindrome, right? And then we could just return first, last match, and sub is palindrome. This breaks it up a little more. And another thing, I'll answer that question in a second. Because of the way that we're checking this, we don't actually need this base case here, right? If len of s is equal to 1, always return true, because that's kind of handled implicitly by our inductive step. In other words, if we ever get to a case where we only have one character, then this will be true, right? Because the first and the last character will trivially be the same because they refer to the same character. And is palindrome, this will just run on an empty string. And by this base case, that'll also be true, right? So we don't actually need this extra base case right here in the way we've written this up. Yeah, there was a question?
This is that a shorter way of like instead of going to every single letter, you just compress it to check the first and the last and then like instead of checking the first and the last and then number 2 with
Like the second and the second to last and the third to last. Yeah, so it's not this short, you're talking about this shorthand right here, right? Oh yeah, yeah. When I had the return statement that looked, so here we have this. So before I had a return statement that looked like return S0 equals S -1 and is palindrome on S1 up to -1. Yeah, so what was your question about this?
and you see the like the last and the first and the second or last.
So not exactly. What this is saying, this statement here, which is exactly the same as this stuff that I've written out a little more explicitly before it, all it's saying is check the first and the last, that these are equal, and that the substring in the middle is a palindrome. The actual checking of each of these characters matching in the middle happens in the recursive subproblems, right? When we call this, like the first time we call uh, sub is palindrome, like on the whole string, this is what ends up being S1 to -1, right? And the second time we call it, right? This is the recursive call on the second time we call it. Then this ends up being the recursive, like the substring S11. And we check if this first character and this last character match, right? And then the third time, it's just E and we check if C and C match, you know? So
Say after, step, then remove the last ones, or not just.
yeah. So the removal of the last ones happens implicitly here. When I call this function recursively, I'm only passing it the substring, right? I'm only giving it the thing in the middle. So it's not aware of what R is anymore, right? Good question. There's another question over here. Okay, great, great, cool. Yeah.
Question thing. If we modify S itself instead of putting directly back into the function, like the way I did is like I checked if the last one was equal to the first one, then I modified as using slicing, and then I just put back as. Is it right or is it wrong because it modified the string that we included first time?
So the thing about strings is they are immutable. You can't actually modify a string once you've created it. So when you say that you removed the first and the last characters in the string, what exactly do you mean?
I did I did a line and if the first one that gets to the S minus one, then S equal S slice.
Oh, I see. So you reassigned it to be the, yeah, so that's fine because all you're doing is you're saying like this, like when you pass this string to this function, like this goes back to like the pass by value stuff. But if I have like, if I make a call is palindrome in some code outside of this function, and I give it a string that I call str maybe, then what happens is like, let's say I have some string str that refers to race car, right? And when I feed str to my function, what happens is that a new reference is created that points to the same string. So when you reassign this later to ace car or ace car, all that happens is this pointer changes, but you haven't modified the original string because they're immutable, right? So yeah, if that works, that's like fine. It's a totally valid way of doing it. Yeah. Okay. Any other questions about is palindrome before we move on to the binary tree stuff? Okay, cool. All right. So we're gonna make, I'll wrap problem, here's what I'll do. Binary search tree. So here's the binary tree node code that was provided for this problem, for problems 3 and 4. We're going to start with problem 3. So our goal is going to be to compute the height of a binary search tree. My first question to you guys is, are we clear on what the height of a binary search tree is? No, okay, I see a no. Okay, so we'll illustrate this. So actually, we can actually use what I'll do is this. And then from binary search tree, import tree node. Okay, so we're going to have a root node that I'll just call root. And we'll start in just like a simple toy example of a tree. We'll start by giving it, I don't know, 7. Okay? And then maybe we could also insert a couple things, like we'll insert 4, we'll insert 5, and we can insert 8 too. And so what this tree looks like is this, right? You have 7 at the root, and then it has 2 children, 4 and 8, and then 4 has a right child, 5, right? So the height of this tree, the height of any tree, is defined as the longest path from the root to any of its leaves. Okay? So what is the height of this tree? I see 3. Yeah, it's kind of like a matter of convention, whether you call it 2 or 3. But for this problem, we're going to call it 2. We're going to say if this tree only had 7 in it and nothing else, then we would say it was a tree of height 1. But the height of this tree is 1. We find the longest path or the longest branch, right? So it's going to be 1, 2, 3 is the height of this tree. Does that make sense to everyone? Cool. And if I did this, like if I inserted 3, and then I printed this. Okay, what's the height of this tree? Hmm? Yeah, it's still 3 because the longest path hasn't changed, right? Okay, cool. Uh, so we're gonna write this question, problem 3 is asking you to write a recursive method that computes the height of the binary tree rooted at the node that calls it. Okay? So let's see how to do that. So within our class, we're going to make a new method, and I'm going to call it height, I think is what they told us to call it in the problem. Yeah, height. And it's a method, so we pass itself. Okay, so what is my base case? I saw a hand like flash briefly, and then well, you could at least tell us what you were thinking. It's a good starting point. Yeah, so if we only have one thing in the tree, right, and the height is 1, that's a really good base case because it's very easy to just say, oh, well, the height is just 1, right? So my base case is going to be height 1, or equivalently, another way of saying this is when my node, the node that's calling this, has no children, right? So the way I can check that is I can say if self.left is none and self.right is none, then we just return 1, right? We're a leaf in the tree. A leaf is the name for a node at the bottom of a tree. Okay, so what's left is handling the inductive step. And to do this, again, we have to see where is the Matryoshka doll, right? Like where is the nested recursive structure of this problem? So if I give you a tree like this, right? And let's imagine that we're at some node in this tree, like 4 here, right? Let's say we're at this node. If I know how to compute the height of each of its children, how can I find what the height at this node is? Right? Because here, the inductive assumption, the recursive assumption is that I can find the, oh yeah, I see a hand.
Like here,
Exactly right. It's going to be 1 plus the height of the child that's bigger, right? And the way that I can do that, find what those heights are, is by just recursively calling my method, right? So what I'm going to do is I'm going to say, okay, there's a couple cases we're going to check. We're going to say if, now we're in the inductive case here. So if self.left is none, so this is just the case where I don't have a left child, right? Then it's really easy. I'm just going to return 1 plus self.right. Oh, I can spell. dot height. Oh, and this shouldn't be a method. This is just an attribute. Okay. Otherwise, elif, it's the same as because we're returning. So else, if we're in the case where I have no right subchild, then I just return 1 plus self.left.height. And the last case, right? The last case is when I have two children. What should I return here? What should I write? Yeah.
So then I is superior and then self the right.
Yeah. We have to like do some checking to figure out which one is the bigger one. But a more compact way of doing this is we can use the built-in max function, right? We can say we're going to return 1 plus the max of self dot left dot height and self dot right dot height. I'll go over. And that's how we write this. Yeah. We can test it. You can see, okay, well, if we reload this now, it's on 3. There we go. And then 7. What else did I insert? 4. And then it was 5, 3, 8. We print, looks like this. Now if we do root.height, we get 3. Yeah? And we can even do like root.left and call its height. And we should see, what? Oh, whoops. Yeah, and we get 2. Right? Well, any questions about the height method? Problem 3. Okay. Not. Let's move on to problem 4. So, problem 4, part A. In this problem, we're tasked with adding another method to our binary tree node class. Except what this method does is it gives you what's called the in-order traversal of the tree rooted at that node. And the in-order traversal of a tree is just the list of all of its keys in like insertion, sorted order. What I mean by that, I think it would be easiest if I illustrated this with an example. The in-order traversal of a tree is recursively defined as, first get the in-order traversal of the left subtree, then get the current node, then get the in-order traversal of the right subtree. So what that looks like, illustrate an example on the board here. We go with the example that we had earlier. I think it was 7 at the top. 8, 4, 5, and 3. Then it's kind of you can see the definition is recursive itself of this in-order traversal thing. It's saying, okay, get me the in-order traversal of this subtree, the left subtree, then put 7, then get me the in-order traversal of the right subtree. So what this looks like is in order of the root at 7 plus, or of the node at 4 plus 7, right? And this is the list that I'm constructing, plus, and I'll just write in as a shorthand here, of the thing at B. Okay, now we have to inductively evaluate this. So in order of the thing at 4, right, this is defined as in order of the thing at 3, the node at 3, plus 4, plus in order of the right subtree. That's what this evaluates to. Plus 7 plus, well, this is kind of the base case, right? Because the in order of my left child is empty and the in order of my right child is empty. So all that I'm left with, what this evaluates to is 8. Yeah? Okay, now we have 2 more base cases here because we're at leaves. This evaluates to 3. We carry over the 4 here. This evaluates to 5, 7, 8. So this is the in-order traversal of this tree. Okay? Are we all clear on what the... And you can see why it's called the in-order traversal is because this is a binary search tree and it satisfies the binary tree property, which is that all of my left children are less than this guy and all of my right children are greater than this guy. When you do this traversal this way, you get your elements in sorted order. And that's why in part B, you're asked to implement a sorting algorithm from this. And this sorting algorithm is called tree sort. What's really cool is when we had the demonstration in class where I like handed out cards and I asked you guys to come up with a sorting algorithm, there was one group that thought to sort this way. And I thought that was really neat. Yeah. Okay, so any questions about in-order traversal? Like the in-order traversal, like what's going on here? Cool, all right, in that case, let's see how to actually code this up. So we're going to add another method here called in-order. We went over the base case a second ago. What was it? It was the same as for height. It's just when we have no children, right? So, okay. If self.left is none and self.right is none, then what should I return? What do I return in my base case when I have no children? Yeah. Yeah, exactly. It's just the list containing self.value and nothing else, right? All clear on that? Okay, that leaves me with my inductive case. We're going to break it into 3 subcases the way that we did before. Okay, so if self.left is none, then in this case, the thing that maybe there's a better way that I can do this. Hold on. Yeah, we'll do it this way. We'll say that left in order. Ooh, maybe I'll do it like, we'll do it this way. We'll say left in order. We're going to initialize this to an empty string. And only if this is not none will we set left in order to be self.left.in order. Yeah? And we'll do the same thing with the right. So the right in order will initialize to be an empty tree. And then if, oh, there's a typo here. If self.right is not none, only in this case do we actually try and get what its in-order traversal actually is. Right in order is equal to self.right in order. And so what my final return statement is going to be, what should I return? Now that I have the left in order, right, and I have the right in order, in other words, this and this, what should the final return statement look like? Yes, in the back.
Left in order self.value, this plus right.
Exactly right. It's going to be left in order. Whoa. Plus self.value in a list plus right in order. And there it is. That's the whole thing. And so to build off of this, or sorry, any questions about this first? Like any of the stuff that I've written here? Yeah, well, oh yeah.
So, yeah, the list is equal to one element at the time, so doing happened. We didn't like it could not like replace what was previously there.
Oh, sorry. The question was,
And the fact that like you like at each time left in order people like some dot left, like it could not like replace what was already in the list.
we'll replace what was already in the list before. Well, what was in the list before was just nothing, right?
Like, we did one now, so I'm not.
If there was just like a single node, the question is if it was like the whole tree was just a single node.
No.
Oh, if there are multiple nodes, so like in this case, yeah.
Yeah. Like what will happen with zero?
So yeah, let's so when we call this method that we've just written on the root here, 7, what it does is it it finds left in order of the tree rooted at 4. It finds right in order the tree rooted at 8, and it appends the thing at the actual value in the middle, and it returns this whole thing, right? But what this evaluates to recursively is this. Or what this evaluates to recursively is this, right? Does that make sense?
Yeah.
Yeah, question.
How come, since we're always setting left in order, we empty usually, every time we do recursively again, when did we set it?
Oh yeah, so these left in order and right in order are not preserved across recursive calls, right? Like the left in order here is the tree is like the in order traversal of the tree rooted at 4. But on this recursive subcall, left in order is the tree rooted at 3. Right? Like these are just temporary placeholder values. Like I could have, done this in one line, I think. It would have looked a lot messier and I would have had to use some syntactic sugar, but yeah, they're just placeholders for this final return string. Or not string, list. Any other questions about this? Yeah.
Like, there's no like comparison or anything.
Yeah.
It's just like writing it. I don't know if it makes sense.
No, it does. It does. It's a good question. It's like, okay, well, where is the actual comparison for finding this?
Or, like, you don't need to, because I guess it's already like in.
Exactly. The comparisons and the fact that it's in all that structure, that happened while we were inserting into the tree, right? So when I traverse like this, I don't have to do any comparisons at all. I just get to reap the fruits of my labor when I was actually inserting stuff into the tree. Yeah. Okay, so part B, which is the slight addenda to this, is, we've already implemented, like, this looks like a sorting algorithm, right? So let's make it an actual sorting algorithm. At the very bottom of this whole mess here, I'm going to define a function, which I'll call tree sort, and it will accept a list. And all it's going to do is it's going to step through this list one at a time. So for element in list, well, I guess we'll do it this way. So we're going to try to do root equals binary tree node of LST 0. Okay. And if this breaks because LST is an empty list and there is no 0th element to index to, then the thing that we're going to accept is an index error. Bless you. And in this case, we'll just return an empty list, right? So the only way that this exception happens is if there is no 0th element, and that means list was empty. So the sorted version of an empty list is just the empty list. That's all this is saying, right? And so now we'll just say for everything in list from the first element onwards, right? Because I've already added the first thing. We'll just do root.insert lm. And then we return root.inorder. And that's my whole sorting algorithm. So we've really exploited the already sorted structure of the tree to write a very nifty, clean, short little sorting algorithm from this. Yeah? Yeah, question.
It says that it doesn't, it's plus sign. You can say that like you can't do that for instant list types.
Oh, maybe there's like a syntax, maybe there's an error here in what I wrote. Let's actually try to run this and see what we get. Okay, so we'll do Python 3, search tree. Okay, no syntax errors, that's good. And now let's actually try to run this. So we'll have some root is equal to a. Actually, and just so that I don't have to retype this a whole bunch, I'll do it like this. Oh, shoot. I should have said quit problem 3 tester dot py. So we'll say from binary search, I think I called it this, tree, import binary tree node. And now we'll say root is going to be equal to binary tree node looks like this. And then we'll insert things, root.insert. I think it was like 4, root.insert 5, 8, 3. And then we'll do print tree so that we can see what the tree looks like. And then we'll actually try doing print the in-order traversal will look like, and then we can just do print root.inorder. Okay, so let's try running this. Okay. And if I try to run Python 3 problem 3 tester now. Yeah, okay, so it looks like it works. Here's our tree, here's what it looks like. And then there's the in-order traversal, right? 3, 4, 5, 7, and then 8 afterwards. So it could be that the problem is a transcription issue in the code that you've written. But yeah, we could take a closer look after class to figure that out and see what's up. Yeah, so you can see, oh, if it looks a lot like a sorted list, it's because it is a sorted list, right? If we wanted to change this into an actual, like here's some, we could do a sample list now looks like, and then we can do, just to make things interesting, let's import random. And then we'll create a random list that looks like random.randint containing things from 0 to 10 or so this is just going to give me 10 random numbers between 0 and 10. And then we'll print what list looks like. And we can say the sorted version looks like, and then lst, or it would be print tree sort on my list. And I actually need to import tree sort as well. Now, if I try to run this, here's the random list that I was given, right? And then the sorted version looks like this. But you'll note that it's not quite the same list because in the way that we implemented this binary search tree, we ignored duplicates, right? Like if I got to the right insertion point in a tree and there was the same value already there, I just did nothing, right? Because it was already there. So in order to make this a true sorting algorithm that preserves duplicates, we would need to change our insert function to also insert duplicate elements into our tree. And there's a really easy way of doing this, which is if I just change this, right? I get rid of this else statement and I replace this with less than or equal to. It's saying in the case where there is a match and it is the same value, treat it as if it's greater. So just add it as the right child. Okay, so now we've changed our tree to handle insertions of the same element. And if I rerun this now, then here I had duplicate elements 0, 0, and they were actually preserved in the tree. Okay? Any questions about problems 3 and 4? Make sense to everyone? Okay. As a fun exercise for yourself, if you want to test how well you understood last week's material, you can try and ask yourself, what is the worst case runtime, asymptotic runtime of tree sort? What is its average case runtime? Yeah, see if you could think about that a little bit, and then if you think you have an answer, come see me and I can tell you what it is, or look it up on the internet. I don't know. I'm not teaching you anything particularly groundbreaking here, but yeah. Okay, cool. Well, if there are no questions about this, let's get on to the dreaded problem 5. Right? I think this problem maybe gave people some trouble. Okay, cool. So problem 5.py. All right, what is problem 5 actually asking us to do? So it's asking us to write a recursive function that returns every possible subset of some input set S. Okay? So to illustrate this concretely, I'm going to do an example on the board because I think that'll help drive the point home for everyone. So my input is going to be a set, I'll call it S. Okay, so maybe my S looks like 1, 2, and 3. So another name for what this function is asking you to compute, and you'll probably encounter this if you take, or if you've already taken introductory discrete math classes or set theory, is it's asking you to find the power set of S. And the power set's just another name for the set of all subsets of a given set, right? So what my return value should look like for this is I want to return a list containing all the possible subsets. So what's a subset of this set? Someone just shout out any random subset.
1.
1, yeah, okay, cool. The set containing 1. Give me another. 2, okay, great. I hear 2, going for 2. Do I hear 3? 3, somebody saying 3 in the audience, no? 3? Okay, 3. Okay, give me another.
1, 2.
Yeah, the whole thing, right? That's a set is a subset of itself. Okay, what's left?
1, 2.
1 and 2. 1 and 2. Another.
Plus 3.
What was it?
Plus 3.
1, 3, yeah. And there's one more. Exactly. Like right. 2, 3. So this is the list containing the power set of S, right? Here we have all my subsets of size 1, all my subsets of size 3, and all my subsets of size 2. But there's actually, I see a couple hands. I think you guys are going to say, yeah, the empty set. It's not done until we also include the empty set. So all my subsets of size 1, or yeah, size 1, of size 3, of size 2, and of size 0. Because the empty set is a subset of every set. It's the only set with this property. So this is what I want to return, right? This is, now I just have to find a way to do it recursively. Does anyone see the Matryoshka doll? Like, where could it be hiding in this problem? So maybe to illustrate it, another way of looking at this whole thing here we'll ask ourselves the question that we should always ask ourselves. We start looking at a recursive problem is, what is my base case? Yeah? An empty set. Exactly, right? When I have the empty set, I just return it, right? Okay, so my base case, and this suggests that n for this recursive problem is going to be the size of the set, the number of things in the set, right? Okay, so what if S only contains a single element? Right? Then my subsets should just be the empty set and the set itself. Right? So we see the empty set, that base case, re-emerging in this bigger subproblem. Okay. What about when I have 2 elements? Is there a way that we can state the power set of this set in terms of the power sets of its subsets? Because that's what is ultimately going on here recursively, right? Maybe we could do it like this. So I'm giving you a magical function that gets all the power sets of smaller, like strictly smaller subproblems, right? So strictly smaller subsets. So my strictly smaller subsets here only contain a single element, right? So another way of writing this is I can say, okay, well, it's equal to, I'm going to use this notation P, capital P, to denote the power set. This is, you can just think of this as like, this is what our recursive function all subsets is trying to compute. So it's going to be P of 1 union P of 2 union, what's missing? Because this, right, like this power set, as we saw earlier, when it contains a single element, is just the empty set and the thing itself, right? So already we have the empty set down. Right, we have that. We have 1. Check. Because of this, right? So this is what P of 1 gives me. And then P of 2 gives me the empty set again, but I already have that, so we're good. What its contribution is 2. right? So if I wanted the power set of this whole thing, and I have this so far, what's missing? Yeah, exactly. 1, 2. So I'll just add S. Yeah? And so this is where the recursion is kicking in, right? If I want the power set of a set, it's enough for me to take the union of the set itself. I guess I should technically say it's the set containing the set, right? The set itself and the power set of all of its subsets of length 1 less than, or of size 1 less than S. Yeah? So that's going to be how we approach this. All right. So, whoop, all subsets. I'll get rid of this. I don't think we need this anymore. Okay, so we want to return a list, right? So what we're going to do is we're going to define some running power set that we're going to build, okay? And in the beginning, we'll initialize this to be the empty set. And then what we want to do is we kind of want to go through the subsets of size 1 less than S and take each of their power sets, right? That's the recursive step that's going on. So what we're going to do is we're going to say for each element in S, we are going to add all of the subsets that this power set on the subcase gives me, right? The subproblem. So we're going to say, okay, power set dot extend. Remember the extend method? It's just like append, but it appends everything in a list that you give it, right? So it'll be extend S minus element, right? So the subset that we're passing it here, in this case, is S without 2. And that gives me this subproblem, right? And the next one, it's going to be S without 1. So we want to go through each of the elements and get the power sets of the set without that element, right? Okay. And now, as we illustrated a second ago, there's one subset that this loop doesn't capture, right? And that's the actual set itself. So then we just power set dot append S, the whole thing, right? Then we return power set. I claim this is it, but it looks a little different from recursive solutions we've seen so far, right? Because where's the base case? It's there. It's not as obvious as in some of the problems, but I promise you the base case is there. Does anyone see where it is, kind of? Where is my base case happening? When S is empty, why is this still returning correctly? Yeah?
Because S would be a empty set, and so like the loop will like run.
Yeah, this loop never runs, right? When S is in the, so the base case is implicitly handled by this loop just never running. Exactly right. So if I try and run this, okay, let's actually try and on 3 problem. I think this is okay, yeah, no syntax errors. So if I try and run this now, let's say let's do this example. S is equal to 1 and 2. Okay? If I try and run this and I say from problem 5 import all subsets. Okay. And I call all subsets on S. Okay. Something a little funky is going on here. It kind of looks sort of mostly right. But I'm not actually getting the empty set here. And the reason why is because what I actually forgot to do is this, right? So we know that the power set will always contain the empty set. So if I do this now, and I try running this again, oh, I gotta quit, reload. Oh, and then the other issue is that my set, it's appending the set itself, but not the individual elements in the set, which is a little weird. Okay, well, anyway, we'll deal with that when we get there. I need to import this, and then S will be as before. That's not what I wanted to run. Okay, yeah, so there it is, right? We have the empty set, 2, 1, and then the whole set, right? Okay, let's try this with 3 things. If I do S is equal to 1, 2, and 3, now I try and call this, then this isn't doing what I wanted to, right? It's getting all the subsets of length 1, or of size 1, and the whole thing, but I'm not getting the subsets of size 2 that I had a second ago, right? Where is this breaking? What am I doing wrong here? What am I doing wrong? Yeah. Oh, yeah. See, that wasn't a rhetorical question. I was like, genuinely help me, please. Where have I made a mistake? And it's because we haven't actually called the power set, right? Duh. Okay, so what we actually want is we want to do all subsets of this, right? Okay, now it's recursive. So if we try this again, okay, we'll do this. Now we do all subsets of S. Whoa! Well, I mean, it's right, right? Like we have 2, 3 in there. We have 1, 3 in there. We have 1. Okay, let's check. Do we have all of our subsets of size 1? I see 1. I see 3. I see 2. So those guys are good. We definitely have the empty set in there a whole bunch. Do I have all my subsets of size 2? Well, there's 2, 3. There's 1, 2. 2, 3, 1, 2. Do we see 1, 3 in here? Where? Yeah. It's where?
You were like right next to it earlier.
I was right next to it.
Passing.
Oh yeah, there we go. Okay, so 1, 3's in there, and we have 1, 2, and 3, right? So everything that I want to be in there is in there. It just contains a whole bunch of duplicates, right? Where are these duplicates coming from? Yeah?
Every time.
Yeah, right. It's like there's a lot of ways that in this recursion that I'm getting to the empty set, right? I'm getting the empty set when I peel 1, or like just for this example, right? Like if we do this example, S equals 1, 2, I should get a whole bunch of duplicates. Yeah, so there's a lot of ways that I'm getting the empty set when I do this. I'm getting the empty set when I strip 1 away and I'm left with 2 because it has the empty set in here, right? And I'm also getting it when I strip 2 away and I call on 1 because it also has the empty set in here. So I have all this extra junk, right? And so the way that I handled this in the actual solution that I submitted was there is a way. There is a way that we saw how to remove duplicate elements from a list. Yeah, it was a set, right? If instead of using a list here, we just throw everything into a set, then we'll never add duplicate elements, right? The only problem is that sets need their elements to be immutable, right? And the sets that we're using right now, they are not immutable. But there is a variant of the set data structure in the Python stable standard library called a frozen set that is exactly like a set. It works exactly the same way, except you can't change it after you create it. It's immutable, right? And you can have a set, you can't have a set of sets in Python, but you can have a set of frozen sets. Okay? So let's see how to modify this so that actually what I'm getting is a set of frozen sets instead. All right. I think like the way that I actually handled this in the solution, if I remember correctly, was I turned this into a helper function. I said, okay, this is actually going to be the helper function. And then what I'm calling here is the helper function. And then my actual all subsets method, what it does is first it gets me the subsets with duplicates by calling all subsets helper, right, on S. But if I want to convert this into without duplicates, then I'll just use a set comprehension to say that it's going to be frozen set, right? This is the frozen set constructor. You can give it a set and it'll convert it to a frozen set for you. Sub for sub in subs with, go to a new line here. With duplicates. There we go. So this will give me a set of frozen sets. And then to return back a list, because that's still what the problem is asking for, I just need to convert this subs without duplicates to a list of sets again. So I'll do a list comprehension for this. I'll say, okay, well, it's a set. I'm going to convert back to a set now of sub for sub in subs without duplicates. Okay, and then I convert back. So this we convert to a set of frozen sets to eliminate duplicates. And now convert back to a list of sets. Okay, so if I run this now, I do quit on 3. Okay, so we'll do from problem 5. Oh, I don't actually, hold on, let me check something. Does this work? Like, are there syntax errors? No, good. So now we'll do from problem 5, put stuff in there. Now let's say my set S is just 1, 2 again. If I call all subsets on S, there we go. Now I've gotten rid of all those pesky duplicates with this, right? So this is just one, like, you didn't have to eliminate duplicates this way. Like, there were other ways of doing it. In fact, really, the smart thing to do would, rather than keeping track of all those duplicates all along, it would be better if you could use frozen sets within the actual recursive function so that you're never adding them to begin with, right? Rather than converting them all at the end. But just for the sake of preserving what we've already written, I've done it this way. And even then, there's like other ways of getting rid of duplicates that don't rely on sets and frozen sets that you could have done. This is just one way of doing it that allows me to illustrate to you what frozen sets are. Yeah. Okay. Question?
Here we use the loop, right? And the curtain
Yeah.
to be able to access things instead. Some of the questions you found that they're very explicit that we should not use the loop.
Oh, that's a good question. So this is, even though this contains a loop, it's still a recursive solution, right? So on a quiz or something, I would word it more carefully. I wouldn't just say you aren't allowed to use a loop. I would have to think about how to state that explicitly. I would say that you have to use recursion, like you have to make a call to the method in some non-trivial. I'll think of like a good way of wording that so that this sort of situation doesn't confuse you if that were to arise on a quiz. Yeah, question in the back? Oh, wow. Okay, yeah, thanks. This is actually a typo on my part. This is an empty dictionary. It should actually be this. Thanks. Yeah. Although, I guess it I think it's still printed as set because we were converting in this step. So even though it was a dictionary, but yeah, you're right. Technically, it should be this because empty curly braces means a dictionary, not a set. So thank you for pointing that out. Yeah. Yeah, was there a question here as well? Or yeah. A way to do it without a loop. Huh. That's a good question. If there's a way to do it without a loop, it's not obvious to me now. Because in some sense, you need to to get every subset of size n-1, you kind of need to go over each element and remove it, right? So it's not, I'm not sure. I don't think there's a way of doing it without any loop at all, but oh, maybe you could do something where, oh yeah, maybe if you just, no, I don't think that would work. I was thinking like maybe you can just remove one, like the element at the start and then somehow, yeah, no, I don't know. I'm not sure. I don't think so, but do you have a solution that doesn't use a loop? Okay, that I would have been excited to see it. Yeah. Yeah. I'll find a clear way of wording that on the quiz. Yeah. If a problem like this were to come up. Another question. Yeah.
Really great, but works that.
Oh yeah, like here?
Yeah, is there a way, well, no, not in the actual app.
Oh,
Up the trophy breaks.
oh yeah.
Set. Is there a way to sort of like add the curly brace or like why does this happen like that?
This happens because empty like sets and dictionaries use the same closing symbols, right? They both use curly braces. So what an empty pair of curly braces means, Python had to pick one, right? They were like, okay, they just defined it to be an empty dictionary. It could have been an empty set, but they defined it to be an empty dictionary. And they left defining an empty set to writing it this way, where it's just like set and then the set constructor and then nothing inside it. Yeah. Any other questions about any of this stuff? All the solutions were posted like before the lecture, so yeah, feel free to go over those. They're a little more well annotated in terms of comments than the stuff that we banged out today, but the solutions and the approaches are the exact same. Okay, well, in that case, we finished like 4 minutes ahead. I don't think we can realistically dive into another one of the problems, so maybe we just end the lecture now. The solutions for 1 and 6 are posted, so you can see them there. But yeah, I guess we'll end 4 minutes early today. Well, I'll see you guys Friday.